Welcome to Basic Thermodynamics class. So we are discussing a chapter 2 thermodynamic process of the second class. So in the last class we discussed about the constant volume process and numerical problems. So in this class we will discuss about the constant pressure process and the problems related to the constant pressure process. So before going to today's class, just we recollect what we told in the yesterday's class. So in the previous class, we have studied about list of thermodynamic process, expression for the work done in constant volume process, and problems on a constant volume process. So thermodynamic process means a non-flow process and a flow process. In coming to the non-flow process, so it has 7 types of a process. The first one is a constant volume or the isochoric or isometric process. These have two names, isometric or isochoric. Second one is a constant volume process. Third one, constant temperature process. This is an isothermal or hyperbolic process. Adiabatic process, that is a isentropic process. Polytropic process, throttling process, and the free expansion. These are the 7 types. So we have to discussed in the second chapter. So in the last class I discussed about only one process, that is a constant volume process. In this class we will discuss about the constant pressure process. So just in 2 minutes I will discuss about the constant volume process. In the constant volume process we are considering the closed system. So the closed system means heat is only transfer takes place, there is no mass transfer. So the volume remains constant. If volume remains a constant means work done by the system is equal to the 0. Work done by the system is equal to the 0. So dq is equal to du. So at constant volume, so P is directly proportional to the temperature. As the pressure increases, temperature increases. As the pressure decreases, temperature decreases. So this is a constant volume process. So some problems we solve about the constant volume process. So coming to the today's class, we will discuss about the constant pressure process. So in this class, on the completion of this bit, you would be able to understand what is a constant pressure process and the expression for the work done and in constant pressure process, solving the problems on a constant pressure process. So in this class we will discuss about the constant pressure process and the expression for the work done. So after work done, so we will calculate the calculate the heat energy and enthalpy also. So enthalpy and the relations between the pressure, volume and temperature also, solving the problems on constant pressure process. So just we move on to the next slide. Next, constant pressure process is also called an isobaric process. Constant pressure process or isobaric. So the term isobaric itself indicates that iso means same. The meaning of iso means same. Bar means it's a pressure unit. So it we call as the same pressure. So same pressure. It means constant pressure. We call as an isobaric process. Isobaric process. So here the in a constant pressure, we are putting the pressure remains constant throughout the process. So we are considering the constant pressure. That's why we are putting the pressure as a constant throughout the process. So the gas contained in the cylinder and the piston arrangement is an example of a constant pressure process. As we all know, in the last class, in the previous first chapter, we discussed this. The gas contained in the cylinder and the piston arrangement is an example of a constant. So here, so as the heat is supplied, the work is present. So whatever the amount of the heat supplied, we are converting into some by rejecting some amount of the heat, the net work is done. Network is done. So consider the heat is added to the system from an outside source. So here heat is giving to the system from the outside source. So this increases the volume and temperature of the gas with no change in pressure. With no change here, we are keeping as a pressure as a constant. So that's why if you are giving heating to the system, if you are giving heat to the system, their volume and the temperature of the gas increases with there is no change of pressure. As the heat is removing from the system, if you in this case we are giving heat to the system, that's why the volume and temperature are goes on increasing. Or otherwise, if the heat is removed from the system, the volume and the temperature decreases with the, but there is no change in the pressure, but there is no change in pressure here. That so if you are giving heat to the system, if you are giving heat to, this is an open system where the heat and the work mass transfer is there. So if you are giving heat continuously to the system, so here the volume, if this the see this point, this goes on increasing like this. If this goes, this is the, this is system only, this is the volume occupied. If you increase the heat, if the heat is continuously increasing, this is a volume increasing. Heat means definitely the temperature should be increased. So temperature is increased means the system blue line here, see this, the blue line will automatically increases, blue line automatically increases. So here what is we are putting is the pressure as a constant. That's why if a P1, these are the P2, so it is a parallel to the x-axis, but is the volume V1, this is a volume. If you continuously heating means giving temperature more, so T1 is greater than T2. So temperature is increasing, the volume also increasing. Temperature is increasing, volume also increasing. But the one condition is a maintaining, that is a pressure is a constant. But pressure is a constant. Similarly, if the heat is removed from the gas to the surroundings of the system, there will be a decrease in volume and temperature of the gas, and there is no change of pressure. So already I told before, in the last slide, if you remove heat from the gas, if you remove heat from the gas, means that the temperature is decreasing. Temperature is decreasing means the volume is also automatically decreases, and but there is a no change in the pressure. If you heat is supplying to the system, heat is supplying to the system means the temperature is increases. If the temperature increases, the volume is also increases, but the condition is that there is no change in pressure. Similarly, if the heat is removed from the gas to the surroundings of the system, there will be decrease in volume and temperature of the gas, and there is no change in pressure, there is no change in pressure. So this is the, here that the volume and the temperature is go. So expression for the see the graph, PV graph for the constant pressure process. As the heat is supplied, the gas will expand from state 1 to state 2 at constant pressure. See here the gas is expand. Here the volume is increasing from V1 to V2. So if the change, if the gas will expand, the gas will expand from state 1 to the state 2 by maintaining the constant pressure. In the second case, whereas the heat is rejected, work done by the gas W1 to 2, W1 to 2 is equal to integral PdV, integral PdV. We all know that the work done is equal to integral PdV, but here we are putting pressure as a constant. That's why P is a constant, means that's why I am bringing outside. So I am writing as a P integral dV, P integral dV. So what is the integration of dV? Integration of dV is nothing but the V. Here what are the states changing? V1 to V2. So it's a P integral V1 to V2. So substitute here. So upper limit minus lower limit. So therefore the work done is equal to P into V2 minus V1. So this figure shows the constant pressure process. As the heat is supplied, the gas will expand from state 1 to state 2 at constant pressure. So thus the work done by the system is integral V1 to V2 PdV, integral V1 to V2 PdV. So here the integral P1 to this one, integral P, sorry, I will write properly. So integral sorry, integral P dV. Integral the state 1 changing from state V1 to state V2. P dV. P dV. So here the P is a constant. So the limits are V1 to V2. So integration of dx, you know that x. So here the limits are there. So limits are there means we have to substitute upper limit minus lower limit. Substitute P is a constant, I am bringing outside. So it becomes a P integration V1 to V2 dV. Since the pressure remains constant, therefore the work done from state 1 to 2 is a P integration of x. You all know that integration of dx is x. So if there is any limits, you can substitute the limits as upper limit minus lower limit. So then the equation comes like a W1 to 2 is a P V2 minus V1. The amount of the work done in terms of a pressure is P into V2 minus V1, where the pressure is a constant and the process is also called as an isobaric process. Isobaric process. Integral W1 to 2 P V2 minus V1. So we can write as a P V2. I am taking this P into inside the bracket. So I am writing this a P V2 minus P V1. So we can, according to the characteristic gas equation or the ideal gas equation, we all know that PV is equal to MRT. PV is equal to MRT. So at the state 2 means it is an MRT2 minus MRT1. So MRT1. So I am taking as a MR common and writing as a T2 minus T1. T2 minus T1. So the amount of the work done is a W is equal to integral V1 V2 P dV. Here the P is a constant. So we are taking the P outside. So P integral dV. So integration of dV is nothing but the V. Integration of dV is the V. So we have to substitute the upper limit minus lower limits. So P V2 minus V1 is another one equation. So we know that the characteristic gas equation PV is equal to MRT, but here it is a PV2. So I am writing as a, here the only pressure is only constant. So pressure volume increases, temperature increases. So PV2 is equal to MRT2 to PV1 is equal to MRT1. So MR bracket open T2 minus T1. So work done can be written as a W is equal to PV2 minus V1 is equal to MRT. So heat supplied in constant pressure process. So according to the non-flow energy equation, Q122 is equal to du plus dw. So we know that we calculate the work done. So work done. So I am writing U2 minus U1 is equal to U2 minus U1 is equal to MCV T2 minus T1. According to the a constant volume process, it is a MCV T2 minus T1 on W is equal to MR T2 minus T1. MR T2 minus T1. So in this we are taking common M T2 minus T1. So here is M T2 minus T1, here M T2 minus T1. So I am taking common is there, and the remaining terms are the remaining terms are CV and R. CV and R. CV and R. After taking the common M T2 minus T1, M T2 minus T1, remaining terms are CV plus R. So we know that Cp minus Cv is equal to R. So I am writing this in terms of a Cp. So this is MCp T2 minus T1, MCp T2 minus T1. So dQ, heat energy supplied. So heat energy supplied is nothing but MCp T2 minus T1. At constant pressure, heat energy supplied is equal to MCp T2 minus T1. So we all know that the non-flow energy equation, according to the first law of thermodynamics, dQ is equal to du plus dW. So we know that at constant volume process, change in internal energy is mCv T2 minus T1 plus mR. From the work done, amount of the work done, we got W is equal to mR T2 minus T1. Here I am taking m T2 minus T1 as a common. After taking the common, so here the remaining is Cv, here the R. So Cv plus R. So m into T2 minus T1 into, we all know that the Cp minus Cv is equal to R. So I am writing in place of a Cv plus R is equal to Cp. So Q122 heat energy supplied, Q is equal to mCp T2 minus T1. Heat energy supplied, Q is equal to mCp T2 minus T1. So change in enthalpy. So during the constant process, heat energy supplied is equal to change in enthalpy. So whereas in the constant pressure process, heat energy is equal to internal energy, at constant process is equal to change in enthalpy. Heat energy supplied is equal to change in enthalpy. So from the definition we can know that, from the first chapter we know that enthalpy H is equal to U plus PV. H is equal to U plus PV. So I am writing these H. So change in enthalpy. So at initial state, H1 is equal to U1 plus P1 V1. At final state, H2 is equal to U2 plus P2 V2. At final state 2, H2 is equal to U2 plus P2 V2. U2 plus P2 V2. So we want change in enthalpy. So change in enthalpy is nothing but H2 minus H1. H2 minus H1 is equal to U2 plus P2 V2, H2 value minus U1 P1 plus P1 V1. So from the definition, H is equal to U plus PV. I am writing at initial state H1 is equal to U1 plus P1 V1. At final state H2 is equal to U2 plus P2 V2. So change in enthalpy means H2 minus H1. So I am writing the total H2 value here, U2 plus P2 V2 minus U1 bracket open U1 plus P1 V1. So I am writing these as a U2 minus U1 plus P2 V2 minus P1. I am writing this as a H2 minus H1 is equal to U2 minus U1 plus P2 V2 minus P1 V1. So previously we know that what is the at constant volume process, U2 minus U1 is equal to how much? mCv T2 minus T1. And again P2 V2 minus P1 V1 I am writing as a mR T2 minus T1. So from constant volume process, U2 minus U1 is equal to mCv T2 minus T1 plus, so I am writing the characteristic gas equation, PV is equal to mRT. So P2 V2 is equal to mRT2, P1 V1 is equal to mRT1. So in the both the terms mR is common, I am taking as a T2 minus T1. So here also m into T2 minus T1 as a common, and the remaining terms are the CV and R. So here also m into change in enthalpy, m in here also m and R are, and the remaining terms are the constant. So I am taking as a m into T2 minus T1 as a constant, and the remaining terms are the CV plus R. CV plus R. So again I can write the Cp minus Cv is equal to R. Cv plus R is equal to Cp. So mCp T2 minus T1. So change in enthalpy. So heat transfer at constant pressure. So dQ is equal to change in enthalpy dH. So dQ is equal to dH is equal to mCp T2 minus T1. Whereas in the case of a constant volume process, change in heat transfer is equal to change in internal energy. So there dQ is equal to du is equal to mCv T2 minus T1. Whereas in the constant pressure process, it is equal to, what is that? Heat transfer at constant pressure is equal to change in enthalpy. Change in enthalpy is mCp T2 minus T1. mCp T2 minus T1. So this is the main difference between the constant pressure and the constant volume process. Whereas in the constant volume process, change in heat transfer at constant volume is equal to change in internal energy, that is equal to mCV T2 minus T1. Whereas in the case of a change in enthalpy at constant pressure process, so heat transfer is equal to change in enthalpy. Change in enthalpy are denoting with capital H. So H2 minus H1 is equal to mCp T2 minus T1. So this is the expression for the work done at a constant pressure process. So this is a constant pressure process. So heat transferred is equal to change in enthalpy. Whereas in that case, heat transferred in the constant volume process, heat transferred is equal to change in internal energy. So coming to the, in terms of a pressure, volume, temperature, we know that the general gas equation or the characteristic gas equation or the ideal gas equation, we know that P1 V1 T1 is equal to P2 V2 T2. So here we are considering the pressure as a constant. So what is the pressure at a constant means P1 equal to P2. So what is the remaining? V1 by T1 is equal to V2 by T2. So the constant pressure process is often referred as an constant pressure process is often referred as an isobaric process. So the in the equation can of state 1 to 2 can be written as a V1 is equal to V2 by T2. Since the gas is heated at constant pressure, P1 is equal to P2. So V1 by T1 is equal to V2 by T2. Here the volume is directly proportional to the temperature. As the volume increases, temperature increases. As the volume decreases, temperature decreases. So V is directly proportional to the T. So the constant pressure process is often called an isobaric process. Isobaric process. So V by T is equal to constant. So this constant pressure process is governed by the Charles law. So in the first chapter we discussed about the Charles law. What the Charles law is at constant pressure. At constant pressure the volume is directly proportional to the temperature. So this is also this, thus the constant pressure process is governed by the Charles law. So V1 by T1 is equal to V2 by T2, or V by T is equal to constant, means V is directly proportional to the T. So if the gas is compressed, the work is done on the gas and heat is rejected. So heat is rejected. So work done by the gas. Here we are taking as a P V2 minus V1. So work done on the gas, heat rejected. In the first case, heat is supplied. If the heat is rejected means it is a negative. So it becomes minus PdV. Minus PdV. So dV means V2 minus V1. But here I am writing as a V1 minus V2. In case of heat rejected, it is a P V1 minus V2 and MR T1 minus T2. Heat rejected also MCP T1 minus some worked examples here. So this is the main difference between the constant pressure and the constant volume process. In the constant volume process, the heat transferred at constant volume is equal to change in internal energy, that is equal to mCV T2 minus T1. Whereas in the case of a constant pressure process, the heat energy supplied at constant pressure is equal to change in enthalpy. So that enthalpy is denoted with capital H. So H2 minus H1 is equal to mCp T2 minus T1. So otherwise in the heat is rejected means the work done will become as a W is equal to minus PdV. So minus we could bring into the inside, it comes as a P V1 minus V2, like MR T1 minus T2, and energy supplied Q is equal to mCp T1 minus T2. So before so so some problems we will do, then we will easily understand the what is a constant pressure process. So here the values of a specific heat at constant volume and characteristic gas constant of an ideal gas are 0.73 kilojoule per kg Kelvin, and 0.25 kilojoule per kg Kelvin respectively. If 1 kg of this gas is heated at constant pressure from 25 degrees to 200 degrees centigrade, estimate the amount of heat added. Heat added means heat supplied they are asking. So read the question carefully and write the data and identify what is the process, which thermodynamic process it is. So the values of specific heat at constant volume. So they given CV and characteristic gas constant R value. So CV value 0.73 kilojoule per kg Kelvin, R value 0.25 kilojoule per kg Kelvin respectively. Mass 1 kg is heated at constant pressure. So here they given the condition, what is that? Just I am highlighting that it is in a constant pressure. So constant pressure, I am highlighting. So thermodynamic process is at constant pressure from 25 degrees centigrade to 300 degrees centigrade. So 25 degrees centigrade. So I am converting into Kelvin. So 25 plus 273 is 298 Kelvin, and the final temperature 200 degrees centigrade, it is a 473 Kelvin. 473 Kelvin. So first write the given data and write what they asked. So here what they asked, just amount of the heat added. So amount of heat added means Q. Q is equal to mCp T2 minus T1. So in this problem they then given that the constant specific heat at constant pressure value, but they given the specific heat at a constant volume and the R value. So we know that the relation between the specific heat and the R, we can calculate Cp value. So what is the relation between the specific heat and the specific heat Cp, Cv and the gas constant R? Cp minus Cv is equal to R. So you know the Cv value and R value. Calculate the Cp value. After calculating the Cp value, what is the amount of the heat added at constant pressure process? Q is equal to mCp T2 minus T1. So you know by M value, Cp value, T2 minus T1, and we will get the amount of the heat added. So the specific heat at constant pressure Cp is equal to R plus Cv. So we will get the Cp value. We will get Cp value. After that, getting the Cp value, in the problem they asked to calculate the amount of the heat added at constant pressure process. So amount of the heat added at the constant pressure process is Q is equal to mCp T2 minus T1. C1 into 0.98 into 473 minus 298. It is 171.5 kilojoules. So the answer is Q is equal to 171.5 kilojoules. So we'll go to the next problem. Here the 1 kg of nitrogen contained in a cylinder at a pressure of 7 bar and temperature 300 Kelvin expands 4 times of its original volume. The process of expansion is assumed to take place at constant pressure. Calculate initial volume, final temperature, work done, heat added. So first read the question carefully. And the given is a condition, it is in a constant pressure. So the constant pressure is a constant means volume is directly proportional to the temperature, and the heat transfer Q is equal to change in enthalpy, that is equal to mCp T2 minus T1. So here what they given? Mass 1 kg of nitrogen, pressure P 7 bar, and converting that 7 bar into 7 into 100 kilonewton per meter square means 700 kilonewton per meter square, and the temperature they given in Kelvin only. So T1 is equal to 300 Kelvin, expands 4 times to its original volume. So V2 is equal to 4 times of V1. So they given the condition. There, what is the condition? So 4 times expands the 4 times of its original volume. So V2 is equal to 4 V1. So the process of the expansion is assumed to take place at constant pressure. So the given that the expansion is takes place at constant pressure, calculate initial volume, final temperature, work done, heat added. So change in internal energy. For the nitrogen, they given the Cp value and the R value also. So initial volume means V1, final temperature means T2, work done dQ is equal to P V2 minus V1, heat added at constant pressure means mCp T2 minus T1, internal energy du is equal to mCv T2 minus T1. So they given the Cp value and the R value. So by using the two values, we can find the Cv value. So first write the given. So first write the given data. So M is equal to 1 kg. So pressure P1 is equal to 7 bar. So I am writing this 7 bar in terms of a kilonewton per meter square. This, if you all know that 1 bar is equal to 10 to the power of 5 Newton per meter square. But I am writing as a 10 to the power of 5 as a 10 square into 10 power 3. 1 10 square is a 7 into 100, and 10 power 3 I am writing as a 7 kilo. P1 is equal to 700 kilonewton per meter square. So temperature T1 is equal to 300 Kelvin. And they given the condition also V2 is equal to, this is 4 times of a V1. So I am writing the V2 by V1 is equal to 4. So at the constant pressure, we all know that the P1 is equal to P2. So 700 kilonewton per meter square. 700 kilonewton per meter square. Cp value 1.045 kilojoule per kg Kelvin. R value, observe that they given the R value in the joule and the Cp value in kilojoule. So we have to convert the joule into kilo. So by simply dividing with 1000, we will get the kilojoule. So 0.296 kilojoule per kg Kelvin. So you have to observe, it's a very careful, because Cp minus Cv is equal to R means both the Cp, Cv and R should be the units same. So one is in joule, another is in kilojoule means, so we didn't get the Cv value as a correct. So you have to check the units before solving the problem and substituting in the formula also. So here they given it is in kilojoules and here in joules. Here it is in kilojoules and here it is in a joules. So we have to convert into kilojoules because here we are taking in the kilo. Here we are taking it in a kilo. That's why we have to convert this also into the kilojoules by simply multiplying and dividing with 1000. So multiplying and dividing with 1000. So in the numerator 1000 I am writing as a kilo. In the denominator 1000 I am writing this as a 0.296 kilojoule per kg Kelvin. So I will tell once again. Simply, if you don't know how to convert the joule into kilo, you all know that the kilo is a 10 power 3 or 1000 kgs. Simply multiply and divided with 1000. Simply multiply and divided with 1000. So in numerator the 1000 can write as a kilo. In denominator 1000 I am writing like this is 0.296 kilojoule per kg Kelvin. So next. So initial volume they ask. So initial volume, how will you get the initial volume? So P1 V1 is equal to MR T1. So we want only the V1. We know the pressure P1 and R value and the T1. So by calculating V1 is equal to MR T1 by P. So substitute M value, R value. So R value should have to taken in kilojoule per kg Kelvin because we are taking the pressure in kilonewton per meter square. So unit should be same. Either have to follow either in Newton per meter square or kilonewton per meter square. Here we are taking kilo means R also we have to take in kilo only. So 0.296 into 300 by 700. So it becomes as a volume. Initial volume is 0.127 meter cube. So they given the condition also V2 is equal to 4 times of V1. So we got the initial volume as a initial volume this much 0.1272 meter cube. So after getting the initial volume we can get the final volume also, that is V2 is equal to 4 V1. Simply multiply with this 4 we will get the final temperature T2. So we want the final temperature T2. So at the constant process, so volume is directly proportional to the temperature. Volume is directly proportional to the temperature. So we can write that V1 by T1 is equal to V2 by T2. So we can write V1 by T1 is equal to V2 by T2. So I am bringing cross multiplying this one because we know the ratio of V2 by V1 is equal to 4 and we want only T1. So T1 is equal to V1 by V2 into T2. T1 T2. So we want the T2. So V2 by V1 is equal to V2 by V1 into T1, cross multiply. So V2 by V1 is equal to ratio is a 4. T1 is a 300. So 4 into 300, 1200 Kelvin. Because we have taken the temperature in Kelvin. So we get the answer is also in Kelvin. If you want in degrees centigrade, simply subtract the answer with minus 273. We will get in degrees centigrade. So if you want in a degree centigrade, simply subtract the answer with 273 degrees. 273 we will get the answer in degrees centigrade. So this is the T to the work done. So work done. So what is the work done? Work done is nothing but at constant pressure P is equal to V2 minus V1. So we know the P value and V2 value and V1 value. So here they given, if you know the V2 value directly we can substitute, otherwise so we know that V2 is equal to 4 V1 minus V1, 3 V1. So you know that the V1 value, simply substitute here. So we get the 703 into 0.1272. So in terms of kilojoules we will get. So work done is equal to 267.12 kilojoules. So we all know that work done at constant pressure process is P V2 minus V1. So we know that P is equal to 700 and the condition they given, that's a condition V2 is equal to 4 V1 minus V1. So 700 into 3 V1. 700 into 3 into 0.1272, it is 267.12 kilojoules. So work done is 267.12. Next one, heat added. So heat added is nothing but the MCP T2 minus T1. MCP T2 minus T1. So M value you know, CP value you know, 1.045. How will you get the CP value? They given in the problem CP value 1.045, 1200 minus 300, so 940.5 kilojoules. This one is a heat added. Change in internal energy. So change in internal energy is nothing but du. So du is equal to dq minus dw. So already we got 940 dq value and dw value. Simply substitute the dq value and dw value, we will get the internal energy, that is 673.38 kilojoules. That is the problem. So just they asked about the work done, heat and the internal energy. So first, according to the characteristic gas equation, P1 V1 by T1 is equal to P2 V2 by T2. It's a constant pressure process. No, V1 by T1 is equal to V2 by T2. So from that calculate the final temperature, and P1 V1 is equal to MR T1. In that calculate the V1 value. After that, amount of the work done is WP V2 minus V1. We will get the work done. Heat energy is Q NCP T2 minus T1. So after getting the W and Q, according to the non-flow energy equation for a constant pressure process, du is equal to dq minus dw. So already we got the dq value and the dw value. Substitute that, we will get the answer. So move on to the next problem. So next problem. So what is the next problem? During the constant pressure process. So they clearly mention here it is in a constant pressure process. Constant pressure process. So first we have to identify what is this process. So during the constant pressure process, the internal energy of 1 kg system increases. 1 kg system is mass 1 kg increases to 28.5 kilojoule, and enthalpy increases means positive 44.3 kilojoules, and the pressure is 620 kilonewton per meter square. So what is the work which accompanies this process? If the initial volume is 0.793 meter cube, what is the final volume? So what is the final volume? So first read the question carefully and identify what is the process. So it is in a constant volume process. So constant pressure process. So I am highlighting here what is the process here means constant pressure process. So mass is 1 kg and the system increases internal energy. So internal energy we are representing with du. Increases means positive 28.5 kilojoules, and enthalpy we are representing with dH. So it is also increases means dH is equal to 44.3 kilojoules, and the pressure here the constant pressure means P1 equal to P2, that equal to 620 kilonewton per meter square. So what is the work which accompanies this process? So W is equal to P V2 minus V1. So we have to calculate the V1 and V2. They given the initial volume. What is the final volume? So first write the given data. At constant pressure process, P is equal to P1 equal to P2 is equal to 620 kilonewton per meter square. Mass 1 kg. U2 minus U1 28.5 kilojoules. Enthalpy H2 minus H1 44.3 kilojoules. So move to the next slide. So for the constant process, heat added is equal to change in enthalpy. So heat added is equal to change in enthalpy, so 44.3 kilojoules. So work done. So work done is equal to Q minus, you can write as a Q, W is equal to Q minus U2 minus U1. So we know that Q value U2 minus U1. So we will get directly W value 44.3 minus 28.5. So minus we will get 15.8 kilo, and volume V1. So second bit V1 0.793 meter cube. This one is meter cube. So they have to calculate the final volume at constant process. Um, constant pressure process W12 is equal to P V2 minus V1. So we know the W value. We know W value, P value and V1 value, and the remaining value is a V2. So substitute all the values in this equation, we will get the V2 value. So 15.8 is equal to 620 V2 minus V1. So bring this 620 to the left hand side, it comes to the denominator. So divide 15.8 divided by 620. After getting this, bring this minus 0.793 to this side, left side, it becomes a plus 0.793. So we will get the answer as a V2 0.82 meter cube. So this is the problem. So in the given problem, they mention that the given what they given change in internal energy and change in enthalpy. So dq is equal to du. So from that you can know, and by using W is equal to W is equal to dq minus du, we find the W value. After finding the W value, we know that W is equal to P V2 minus V1. Substitute the W value here, P value and V2 minus V1, we will get the V2 value 0.82. So what we learned in this means, so in this period we learned about the constant pressure process, and the expression for the work done on a constant pressure process, solving the problems on a constant pressure process. So in the tomorrow's class also we will solve some example problems, on constant pressure process. So what is the main difference between the constant volume and the constant pressure process? Is nothing but the constant volume and the constant pressure process. The constant volume process is called the isochoric process. In the isochoric process, we are in the whole total process, the volume remains constant throughout the process. Whereas in the constant pressure process, how will you differentiate the constant volume and constant pressure? Means I am telling that. Whereas in the constant pressure process, that pressure remains constant throughout the process. Here we are considering for the constant volume closed system, and in a constant pressure process open system. Here that the constant volume, heat and only heat transfer takes place, no mass transfer across the boundary. So the work done by the system is equal to the 0. Work done by the system is 0. So W is equal to integral V1 V2 PdV is equal to 0, where dV is equal to 0. So the work done is equal to 0. Then dQ is equal to U2 minus U1. So you can write as a mCV T2 minus T1. So whereas the volume is constant means P by T is equal to constant. So here where the state, initial state 2, therefore we can write the relation between the initial and the final states as a P1 by T1 is equal to P2 by T2. As the pressure increases, the temperature is also goes on increases. As the pressure decreases, temperature decreases. So when the pressure will increases, when the pressure decreases means in the heat supply process the pressure is increases and temperature also increases. Whereas in the case of heat is rejected means the pressure and the temperature is goes on decreasing. Pressure and the temperature is goes on decreases, and this process is also called as an isochoric process or isometric process. Isochoric or isometric. Metric means meter cube. So volume units are meter cube. So that's why we call as a constant volume or isometric process. So coming to the constant pressure process. So here the energy is supplied. So the gas is expanded from the state 1 to state 2. Here we are putting the pressure as a constant. We are taking example as a piston cylinder example. So we are giving heat continuously and the system moves and this volume is continuously increases. If you remove the heat means temperature is decreasing and the volume of the system is shown be decreases. So the amount of the work done when the heat supplied is integral PdV. In case of heat rejected means minus PdV. So W is equal to heat supplied. In case of heat supplied is equal to P V2 minus V1. We can write as MR T2 minus T1. In case of heat energy supplied means Q is equal to mCp T2 minus T1. So net non-flow energy equation. So U2 change in internal energy is equal to dQ minus dW. So I am writing as a mCv T2 minus T1, and the equation can be written also in terms of a V1 by T1 is equal to V2 by T2, and this constant pressure process is also called as an isobaric process. Because iso means same, baric means the units of the pressure. Same pressure, having the same pressure means constant pressure process. So during the constant pressure process the heat energy supplied is equal to change in enthalpy. So H is equal to U plus PV, that H also we got as the same mCp T2 minus T1. So in the next class we will solve some problems, two problems on the constant pressure process, and we discuss about then a isothermal process. So isothermal process is based on a constant temperature. So constant temperature process. So third process is constant temperature or isothermal. Iso means same, thermal means temperature, means maintaining same temperature. So in the next class we will discuss about the iso